Hey folks, going to work through the test 3, the practice test, and here at number 1, I asked you to determine exactly the 6 trig function values for theta equals 11 pi over 6. So remember, this is just going to be a basic unit circle question. Hopefully by now you're starting to see the importance of knowing the unit circle. So let me sketch a quick unit circle. And that's not too bad for me. You need to know where 11 pi over 6 terminates. Hopefully you're getting really proficient with this. And you know 11 pi over 6 terminates about right there. You need to know the coordinates of that point. The x-coordinate is square root 3 over 2. And the y-coordinate is negative 1/2. And then knowing that the x is cosine and the y is sine, you can quickly determine that the sine of 11 pi over 6 is negative 1/2. The cosine of 11 pi over 6 is square root 3 over 2. And then the tangent of 11 pi over 6, which is just sine over cosine, so that's a negative 1/2 over square root 3 over 2, would simplify to negative 1 over square root 3. And then the other 3, we just use the reciprocal identities to get the cosecant of 11 pi over 6 is negative 2. The secant of 11 pi over 6 is 2 over the square root 3, and then cotangent is the reciprocal of tangent, and that gives you negative square root 3. So again, number 1 will be a basic unit circle question. Feel free to always sketch a unit circle and have the points labeled. As you'll see later on as we work through the solution, we keep coming back to the unit circle. It's going to be very helpful in solving trig equations that we'll see here in a little bit. And hopefully that's what you have for number 1. And that's it for number 1. Alright, hey, here in number 2, you were given that the cosine of x is negative 2/3 and the sine of y was 5/7. And both x and y are found in quadrant 2. Find exactly, and then I asked you to find 4 things: the sine of x, cosine of y, cosine of x plus y, and the sine of x plus y. The first thing that I'll make note of is, since you know both x and y are out here in quadrant 2, remember that all students take calculus. So since they're both x and y are out here in quadrant 2, we know that the sine of x will be positive, and we need to find the sine of x. That was part A. And the cosine of y, since y is out here in quadrant 2, cosine of y will be negative. And that's what we were asked to find in part B. So let's do part A, finding the sine of x. To find the sine of x, I come back to the Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. For those of you that are heading off to calculus, I cannot stress how important it is for you to be familiar with these basic identities. And this is a basic Pythagorean identity. That's why you will find me continuing to use these basic identities. It's so that you're proficient when you get to calculus and recognizing the identities. But in any event, for this one, I know cosine of x is negative 2/3, so I toss negative 2/3 in for cosine of x. And when I square negative 2/3, I get a 4/9. I subtract 4/9 from both sides. And that gives me sine of x, or sine squared of x, is equal to 5/9. And then when I take the square root of both sides, I get the sine of x is plus or minus to square root 5 over 3. But since we know x is in quadrant 2 and sine is positive out in quadrant 2, my answer for part A will be the sine of x is the positive square root 5 over 3. So that's the answer for part A. And now I'll have to let you take a look at this. I'm going to erase this so I have room to do part B now. So if you need to write any of this down, that would be a good time to hit pause so you could copy this down, because I'm going to erase. For part B, when I'm trying to find the cosine of y, well, I'm going to do it the same way as I did part A. I'm going to use the Pythagorean identity, cosine squared y plus the sine squared y equals 1. So I can substitute 5/7 in for the sine of y. I get cosine squared y plus a 5/7 squared equals 1. Cosine squared y plus, well, 5/7 squared is 25 over 49. And then I subtract 25 over 49 from both sides to get cosine squared y is equal to 24 over 49. And when I take the square root of both sides, I get cosine of y is plus or minus the square root of 24 over 7. But since we know y is in quadrant 2, that's what was stated in the problem, angle y is out here in quadrant 2. In quadrant 2, cosine is negative. So my answer for part B is the cosine of y is negative square root 24 over 7. So hopefully that's what you had for part B. Cosine of y is negative square root 24 over 7. And that's it for part B. Again, if you need to hit pause to write anything down, feel free to hit pause now, because I'm going to erase part B so I have room to do part C. Okay, in part C, I asked you to find the cosine of x plus y. So this is one of your sum identities. There were sum identities for cosine, sine, as well as difference identities for cosine and sine. This is using the sum identity. So you need to know that you can rewrite cosine of x plus y as cosine of x times the cosine of y minus the sine of x times the sine of y. And let's see, cosine x. We were given cosine x as negative 2/3. So we can just substitute negative 2/3. And for the cosine of x, cosine of y, well, we found cosine of y in part B, and we determined that in part B that the cosine of y was negative square root 24 over 7 minus sine of x. In part A, we determined what sine of x was. So from part A, we determined sine of x was square root 5 over 3. So sine of x is square root 5 over 3. And finally, sine of y, well, that was given to us. It's 5/7. So all that's left to do is just this basic multiplication. Take negative 2/3 times negative square root 24 over 7 to get 2 square root 24 over 21. 3 times 7 is 21. Minus 5 square root 5 over 21. And then since we already have a common denominator, we ended up with a common denominator here of 21. I would probably go ahead and just make this one fraction, 2 square root 24 minus 5 square root 5 all over 21. And that's what I get for part C. I'm sure there's at least one of you out there that's saying, well, can't you simplify the square root 24? Doesn't that simplify to 2 times square root 6? So shouldn't you have the answer as 4 square root 6 minus 5 square root 5 all over 21? I'm going to say I'm happy with this answer. If you want to go ahead and simplify that radical, I'm not going to stop you. Go ahead and do it. But I am fine with this as an answer. And that's part C. And yes, at this time, hopefully you had part C. And if you need to write anything down, hit pause so you can write it down, because I have to erase this so I can do part D. All right, folks, in part D, we are doing the sine of x plus y. And the key here is knowing the identity for sine of x plus y. Knowing that that identity is the sine of x times the cosine of y plus the cosine of x times the sine of y. And just like we saw in part C, now it's a matter of just substituting in what we know. In part A, we found the sine of x was square root 5 over 3. In part B, we found that the cosine of y is negative square root 24 over 7. We were given that the cosine of x is negative 2/3. And we were given that the sine of y is 5/7. So just as we did in part C, why don't we go ahead and multiply these fractions together to get negative, well, square root 5 times square root 24. 5 times 24 is 120. So that's a negative square root of 120 over 21. And then negative 2/3 times 5/7 is a negative 6/21. So that's a minus 6 over 21. And again, just like in part C, since I have a common denominator, I would go ahead and just make it one fraction, negative square root 120 minus 6 all over 21. And that's what you should not have for part D. You should not have this. It helps if I can do basic multiplication. Negative 2 times 5 that's a 10, not a 6. So you should have had a 10 there. And you should have a 10 here. So, and I have no idea how I would have gotten a 6 there, other than I haven't had enough coffee today. So hopefully this is what you have. Negative square root 120 minus 10 all over 21. And that concludes number 2. That's the final part, part D. So hopefully at this time you had all parts in number 2, and things are going well for you on the review. That's it for 2. Hey folks, here in number 3, you were given the sine of x is 5/7, and you were told cosine of x is a negative number. Cosine of x is less than 0. And you were asked to find, in part A, the sine of 2x. Well, here we're working with our double angle identities. So you need to know that the sine of 2x is 2 times the sine of x times the cosine of x. We already know what the sine of x is. You know sine of x is 5/7. So we already have the sine of x is 5/7. What we don't know is the cosine of x. And by this point in time, hopefully you're seeing that I need to get the cosine of x. I need to get what that exact value is. And since I know the sine of x, to get the cosine of x, I'm going to use the Pythagorean identity. Cosine squared x plus sine squared x equals 1. All I have to do is substitute 5/7 in for sine, and I have cosine squared x plus a 5/7 squared equals 1. Cosine squared x plus 25 over 49 is equal to 1. Subtract 25 over 49 from both sides. And then take the square root. And I get cosine x equals plus or minus the square root 24 over 7. But for this problem, since we're told cosine is negative, I will use the cosine x is the negative square root 24 over 7. So cosine x is negative square root 24 over 7. So my sine of 2x is 2 times the sine of x, 5/7, times the cosine of x, which is negative square root 24 over 7. I multiply those three together. 2 times 5 is 10, times that negative gives me a negative 10 square root 24 over 49. And hopefully that's what you have for part A. For part B, I think I have enough room to get part B in here. You're asked to find the cosine of 2x. You have three different identities for the cosine of 2x. You need to know all three identities for cosine 2x. So quickly, let's review those. You need to know the cosine of 2x equals cosine squared x minus sine squared x, or cosine 2x equals 2 cosine squared x minus 1, or cosine 2x equals 1 minus 2 sine squared x. Technically, I can use any one of those three for this problem to get the cosine of 2x. The one I will use is that cosine 2x is 1 minus 2 sine squared x. And the reason I use this one is quite simply, I can use this because I was given what sine x is. This identity allows me to use the given information. So if I had made a careless mistake over here in determining cosine x, I made a careless subtraction error, like I did in the last problem. If I had made a careless mistake, that careless mistake won't be used again here. I am using given information. So just simply substitute in 5/7 for the sine of x, and when you take 5/7 and square it, you get 25 over 49, and that's 1 minus 50 over 49. And 1 minus 50 over 49 should give you a negative 1/49. So hopefully for part A, you got the sine of 2x is negative 10 square root 24 over 49. And for part B, you got the cosine of 2x is negative 1 over 49. And that's it for number 3. All right, hey folks, here at number 4, I give you a total of 6 equations, and I asked you to solve them in the interval 0 to 2 pi. And I will ask you to do this on the test. Quite simply, I just want to know, or anyone would want to know the answers in the interval 0 to 2 pi, because that's one trip around the unit circle. So we are finding distinct solutions. I know some of them in the book, you had to write them like all solutions with like a multiple of pi over 2 or pi with a k tossed in there. We're not doing that here. We're just solving in the interval 0 to 2 pi. So in part A, the equation I gave you was 2 cosine x plus square root 3 equals 0. And to solve this one, I'd start off by subtracting square root 3 from both sides of the equation. And then I divide both sides of the equation by 2. And I get cosine x is equal to negative square root 3 over 2. And, all of these equations that we're solving here in number 4, they all come back to one basic structure. the unit circle. Knowing the unit circle. Knowing, now let me try to sketch another unit circle. And that's still not too bad for me. Knowing that on the unit circle, cosine matches up with an x-coordinate. And knowing that it's this point on the unit circle that will have an x-coordinate of negative square root 3 over 2, and this point on the unit circle that will have an x-coordinate of negative square root 3 over 2. If you know that, then you know that the answer to this question, or that the solution to this equation, matches up with this angle here, which is 5 pi over 6, and this angle here, which is 7 pi over 6. And those are, quite simply, the two solutions to this equation. And because I'm going to need a unit circle, or I'm going to refer to the unit circle in parts B, C, D, E, and F, all 6 parts here, I'm going to leave that unit circle up here, and I'm going to have to erase this. So if you need to write anything down, just like before, now would be a good time to hit pause, because I'm going to erase it. See, here in part B, you were asked to solve sine squared x plus sine x equals 0. Probably the first thing I would do in solving this equation is, on the left side, I would just go ahead and I would factor out a sine x. And then once I factored it out, I would take each one of these factors and set equal to 0. So I have sine x equals 0, sine x plus 1 equals 0. And, well, we're coming back to the unit circle again. Let me erase those points. That was from part A. When I look at this, sine x equals 0, if I know on the unit circle that sine matches up with a y-coordinate on a point, then I know sine has a value of 0 at that point and at that point, because both of those points have a y-coordinate of 0. Well, this matches up with an angle of 0, no rotation. And this point here matches up with an angle of pi. For this, we should subtract 1 from both sides. And again, where does sine equal negative 1? Where on the unit circle do you find a y-coordinate of negative 1? Well, that's right down here. If you know it's down here, then you know the angle is 3 pi over 2. And that would be the 3 solutions to the equation in part B. X is 0, pi, and 3 pi over 2. So hopefully you have that for part B. If you need to write anything down, hit pause, because I'm going to erase. In part C, you were asked to solve this quadratic-looking equation. Now, ironically, something like this just popped up on my Calc 1 test that my Calc 1 students took on Friday. They did one step of calculus, and they saw an equation like this that they needed to solve, exactly like this. So yeah, you will see this stuff in calculus. Because it kind of looks quadratic, I would probably start off by saying, well, hey, can I factor it? And so I smacked down, my 2 sets of parentheses, and put a 2 cosine x here, cosine x here. Factors of 1, well, just 1 and 1. That's not too difficult. And it's figuring out if this is a plus or minus and if this is plus or minus. I think we need a minus here and a plus here. And I think this is the factorization of that equation that you were given. And keep in mind, you could always check it real quick, kind of FOIL it out, make sure you do get this. But once you have it factored, you can set each factor equal to 0. So you have 2 cosine x minus 1 equals 0, or cosine x plus 1 equals 0. Add 1 to both sides, and then divide both sides by 2, and you get cosine x is 1/2. Here you subtract 1 from both sides, and you get cosine x is -1. And yes, it comes back to this wonderful structure, the unit circle. So let me erase those from that's what we were looking at in part B. Cosine x is 1/2. Function is cosine on the unit circle. That means that is an x-coordinate. So where would we find an x-coordinate of 1/2 on the unit circle? I believe right up here, and then right down here. So if you know that, you know this has an x-coordinate of 1/2, then you know the angle will be pi over 3. And the angle down here, the angle that would come around and intersect the unit circle down there in quadrant 4, is 5 pi over 3. Where on the unit circle will you find an x-coordinate? This is cosine. Cosine is an x-coordinate. Where will you find an x-coordinate of -1? That's right here, which is at pi. So for part C, hopefully you have the 3 solutions: pi over 3, 5 pi over 3, and pi. And if you need to write anything down, again, hit pause, because I'm going to erase. Part D, I asked you to solve sine 2x plus cosine x equals 0. Okay, a lot of times it's really difficult to solve a trig equation if you have 2 different trig functions involved, like we have here. We have the trig function sine and the trig function cosine. But we can make this problem a little easier if we use our double angle identity for sine 2x. Remember, the double angle identity for sine 2x allows us to rewrite sine 2x as sine of x times cosine x. So once we rewrite sine 2x as 2 sine x cosine x, on the left side of the equation, we see cosine x appears in both of these terms. So why don't we go ahead and factor out a cosine x. And once we factor it out, we can then set each one of these factors equal to 0. So we have cosine x equals 0, or 2 sine x plus 1 equals 0. Or here you would have sine x is -1/2. And that's right, again, I bring it back to the unit circle. Cosine, trig function cosine matches up with an x-coordinate. So where on the unit circle will I find an x-coordinate of 0? Well, I'll find an x-coordinate of 0 on the unit circle right here and right here. That's pi over 2 and 3 pi over 2. So there's 2 solutions, pi over 2 and 3 pi over 2. Here we have sine x equals -1/2. Sine is a y-coordinate. So where on the unit circle will we find a y-coordinate of -1/2? Well, I think we'll find a y-coordinate of -1/2 approximately right here and over here. So if you know where to find them, then you know what the angle is. This angle is 7 pi over 6. And this angle here is 11 pi over 6. So for part D, hopefully you had these four solutions: pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. And again, if you need to hit pause to write anything down, do it, because I'm grabbing the eraser. Okay, part E, you have a cosine 2x plus a sine x equals 0. Well, similar to part D, I'm going to have to use a double angle identity. But remember, cosine 2x has three different ways to rewrite it. It has three different identities. It's the cosine squared x minus sine squared x, 2 cosine squared x minus 1, or 1 minus 2 sine squared x. Out of those three, the one to use here is to rewrite cosine 2x as 1 minus 2 sine squared x. Because that way we end up with a trig equation that has, well, just one trig function in it. That should be a little easier to solve. Now, here's what I would do to this equation. I would rewrite the left side so that we are, so it looks like it's in a descending order. That looks a little better. And, I refuse to try to factor in public something that has a negative leading coefficient. So I'm going to go ahead and multiply both sides of the equation by -1 to get something that is a little easier for me to try to factor. Okay, now I'm going to try to factor this. And, just like before, I smack down my two sets of parentheses. A 2 sine x here, sine x here. 1 only has factors of 1 and 1. I think what you'll find here is I have to have a plus sign and a minus sign. And we could go ahead and we could check this, FOIL it out real quick to make sure it is the correct factorization here. But trust me, it is. Set each factor equal to 0. And subtract 1 from both sides. Divide both sides by 2. Here I'd add 1 to both sides. And again, we are back to a basic unit circle. Said that a lot today. Basic unit circle, knowing that sine is a y-coordinate. Where on the unit circle do you find a y-coordinate of -1/2? And I still have those up from part D, which is kind of interesting. We have the same solutions here as we did in part D. So 7 pi over 6 and 11 pi over 6. Where will we find that sine has a value of 1? Well, that's on the unit circle. Where do we find a y-coordinate with a value of 1? That's right up here. So that's at pi over 2. So in part E, this trig equation had three solutions: 7 pi over 6, 11 pi over 6, and pi over 2. And hopefully you have those three. Again, if you need to write something down, pause it. So I'm getting the eraser so I can make room for part F. All right, hey, here in part F, we have 2 square root 3 sine 2x equals square root 3. I would start off by dividing both sides by 2 square root 3. So that gives me sine 2x equals 1/2. Okay, I know this says sine 2x, but pretend you don't even see a 2x. Let me cover it up with my hand. We're dealing with the trig function sine. Sine matches up with the y-coordinate on the unit circle. So let me cover it up again. Where in the unit circle do you find a y-coordinate of 1/2? Well, you find a y-coordinate of 1/2 about right here and about right here. At pi over 6 and at 5 pi over 6. So let me cover it up again. What must appear behind my hand is pi over 6 or 5 pi over 6. That's what must appear in order to have a true equation. Sine of pi over 6 is 1/2. Sine of 5 pi over 6 is 1/2. So that means what is under my hand, what I'm hiding, must equal pi over 6 or 5 pi over 6. 2x must equal pi over 6 or 5 pi over 6. I'm not done yet. I'm not done for two reasons. One, I eventually need to solve for x. But reason two, this says 2x. Go back to the very beginnings of graphing, when we looked at graphing the trig functions. On the interval 0 to 2 pi, sine of 2x, sine 2x, that has a period of pi. So that means on the interval 0 to 2 pi, sine 2x would make 2 cycles. What that allows us to do, and this is a trick, if you will, it's my little trick, is that because there are 2 cycles on the interval 0 to 2 pi, this 2 is telling me to make 2 trips around my unit circle. On my first trip on the unit circle, I got pi over 6 and 5 pi over 6. On my second trip around the unit circle, I am simply finding angles that are coterminal with these 2 angles. Well, that takes us back to probably the first week of the course, coterminal angles. Coterminal angle with pi over 6. Remember, you have to add 2 pi to that. So pi over 6 plus 2 pi, well, 2 pi is 12 pi over 6. So pi over 6 plus 2 pi is a 13 pi over 6. Add 2 pi to this one and you get 17 pi over 6. But we don't want to know what 2x is. We want to answer the question. When you solve an equation, you always want to know what x is equal to. So we know 2x could equal any of those 4 angles. To get x, you just simply divide each one of those by 2. Or if you prefer, you could think of it as, instead of dividing by 2, multiply each one of them by 1/2 to get pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Notice those are 4 solutions to this equation, and notice that all 4 of these solutions are in the interval 0 to 2 pi. I mean, 17 pi over 12 is definitely less than 2 pi. And yep, that's how I would do part F. Hopefully this is what you have for F. Hopefully you have those 4 solutions. And hopefully you're doing a good job on solving trig equations. That's it for number 4. Hey folks, here in number 5, you were asked to solve 3 more little equations in the interval 0 to 2 pi. I asked you to round your answer to 4 decimal places. The first one was sine theta is 0.35. And yep, sure enough, I am going to bring this back to the unit circle. Keep in mind, talking about the trig function sine, so 0.35 is a y-coordinate. So if I quickly sketch a unit circle, that's a y-coordinate. I'm going to just arbitrarily say, well, I'll find a y-coordinate of 0.35. I'll say about right here. Don't know what the x-coordinate is, I don't care. And then again, another one is over here. So we're trying to find this angle measure, and in order to do that, you're probably thinking, hey, angle finder, I bet I'm going to use an inverse trig function. You're correct. Theta is the inverse sine of 0.35, and if you use your calculator and round it to 4 decimal places, you're going to get thetas about 0.3576. That's what that angle is. But you have another angle. You have another angle that's out here in quadrant 2, where the angle intersects the unit circle at a y-coordinate of 0.35. So you have this angle measurement yet to find. And this is the power, the beauty of the unit circle. These 2 points are symmetric about the y-axis. Because they're symmetric about the y-axis, the magnitude of this angle and this angle, the magnitude is the same. Since these 2 little angles here have the same magnitude, to get this rose-colored angle, I'm going to call this rose-colored chalk, to get this rose-colored angle, I just simply need to come from here to here, which is a measurement of pi, and subtract off the magnitude of that angle. Subtract off the 0.3576 to get, pi minus 0.3576 is, I'm going to say 2.784. So those are the 2 solutions to part A. You need to use your calculator. Make sure your calculator's in radian mode. Part B, I think I have enough room over here for part B. Cosine theta. Cosine theta is 0.56. Yes, again, I'm going to bring it back to unit circle. Unit circle. Let me sketch again a quick unit circle. Cosine. That matches up with an x-coordinate. So where in the unit circle will I find an x-coordinate of 0.56? I'm going to say about right here. It's an x-coordinate of 0.56. I don't know what the y-coordinate is. I don't care. And down here. Here's another point on the unit circle that would have an x-coordinate of 0.56. So our task is to find that angle measure. And hopefully you're thinking, well, use angle finder, use inverse cosine, because you'd be correct. It's inverse cosine of 0.56, and that gives you, let's see, when I use my calculator, I get an angle of about 0.9764. That's that angle there. But yes, there's another angle. There's this angle. That rose-colored angle there. How am I going to find that angle? Again, it's the power of the unit circle, the beauty, the simplicity of the unit circle. These 2 points are symmetric about the x-axis. If I go all the way around, that's an angle measurement of 2 pi. Because these 2 points are symmetric about the x-axis, the magnitude of this angle and the magnitude of that angle right there, they have to have the same magnitude. So to get that angle that I've shaded in rose, or that I've sketched in the rose-colored chalk, I would make one complete trip around the unit circle, which is 2 pi, and then I would subtract off this little angle measurement here. With that little angle measurement there is 0.9764. So I get theta, the rose-colored angle, 2 pi minus 0.9764. I get that to be about 5.3068. So those are the two angles that I get for part B. Okay, part C, as you can see, I don't have room to put part C up here, so I'm going to erase. I assume that you either have this, and you're happy that you have it, or you've written it down already. If not, hit pause, because I'm going to start erasing it. In part C, you are given sine of theta equals negative 0.64. Yes, it's going to come back to the unit circle again. So let's look at a quick unit circle. Sine, that's a y-coordinate. Where on the unit circle will I find a negative y-coordinate? Well, I'll find a negative y-coordinate down here, negative 0.64, and over here. Now keep in mind we're solving in the interval 0 to 2 pi. And the reason why I'm stressing that is while I assume you know to get theta, you're going to do inverse sine of negative 0.64. I remember back on the study of inverse trig functions, an inverse sine rips an angle off the right half of the unit circle. It rips an angle off in the interval negative pi over 2 to pi over 2. When I use my calculator here, I am not surprised to get an angle that is a negative angle measure, negative 0.6945. Your calculator has just told you that angle measure. We cannot use that as an answer. This is a negative number. We want our solutions in the interval 0 to 2 pi. A negative number is not in that interval. So, well, this looks like it's a pretty easy fix. I can't use what the calculator told me, but it's pretty easy for me to get the angle that's coterminal with a negative 0.6945. I just simply add 2 pi to that. So I just simply take this negative 0.6945 and add 2 pi to it, and I get 5.5887. Well, that wasn't too bad, so that's what that angle measure is. But there's another angle. Whoops. We have this angle here. We have to determine what I've sketched the angle in this rose-colored chalk. We have to get that angle measure. The magnitude of this angle is the same as the magnitude of that angle. From here to here is pi. So I just need to simply add on a little bit more to pi. Or, to see what you will be adding on, just like in part A, this rose-colored angle, theta, is pi, there's my pi right here, minus the measure of this angle, which is negative 0.6945. Because when you subtract a negative, you are really adding. Make sure you understand this. It's pi plus 0.6945. This little angle here has a measurement of 0.6945. It's the same magnitude as what that angle was. And you found that angle using your calculator. In any event, when you add this together, you will get the second angle to be 3.8361. So, the two values of theta for part C are 5.5887 and 3.8361. Hopefully you got all this in part, or in number 5, parts A, B, and well, this one was C. Sorry I didn't label that, folks. But I think you knew it was part C. And that's it for number 5. Hopefully you got it. Hey folks, here in number 6, you were asked to solve a triangle. You were given angle B is 58 degrees, angle C is 47 degrees, and side C is 9. So whenever I'm asked to solve a triangle, as long as I know it's not a right triangle, I just kind of draw a generic triangle. All of my triangles would look the same, unless if it's a right triangle. And I just kind of label. I mean, I know angle B is 58 degrees, so I'll put that in there. Angle C is 47 degrees, I'll put that in there. Here's side C. Oh, we know side C is 9, so I'll put that in there. Here's side B, and there's side A. And then remember, to solve a triangle, you have to find 6 bits of information. You have to find the measure of all 3 angles and the length of all 3 sides. So I'll make like a little solution area. It would look something like this. And we know that's 58 degrees, this is 47 degrees, and this is 9. So that's the 3 things that we know, and then we have 3 missing bits to find. Pretty easy to find angle A. I would find angle A next, because we know in a triangle, the 3 angles must add up to 180 degrees. So I'd simply add these 2 angles together, subtract that sum from 180 degrees to get angle A is 75 degrees. Now I have the 2 missing sides, side A and side B. To find both of these sides, I'm going to need the law of sines. So why don't we find side B? And I'm going to need to use the law of sines. Here's how I'd write down the law of sines here. I'd write down B over the sine of angle B equals C over the sine of angle C. So when I substitute in what I know, B over the sine of 58 degrees equals 9 over the sine of 47 degrees. And then I can multiply both sides of this equation by the sine of 58 degrees to get B equals 9 times the sine of 58 degrees over the sine of 47 degrees. And then I'll use my calculator, multiply that out and divide. And I got B to be pretty close. I'm going to round this to 10.4. So B is 10.4. So all that's left is side of A, finding the length of side A, and use the law of sines again. Here I would write down A over the sine of A equals C over the sine of C. So I'd have A over the sine of 75 degrees equals 9 over the sine of 47 degrees. And then I multiply both sides by the sine of 75 degrees to get A equals 9 times the sine of 75 degrees over the sine of 47 degrees. And I use my calculator to finish this off, and I get A is about 11.9. And I now know the length of all 3 sides. I know the measure of all 3 angles. So I guess I've solved the triangle. Before I finish this one, it's just like a reasonability check. Remember that the side that is opposite the largest angle, and here the largest angle is angle A, so the side opposite is side A. Remember, the side that's opposite the largest angle, it must be the longest side, and it is. And the side that's opposite the smallest angle, here the smallest angle is angle C, the side that's opposite the smallest angle must be the shortest side, and it is. So that's at least a reasonability check. It tells me that the answers are reasonable. And then the final thing, I kind of developed this habit when using the law of sines. Whatever it is I'm trying to find, like here I'm trying to find side B, here I was trying to find side A. Whatever it is I'm trying to find, that's what I put in the numerator of the fraction. It saves me 1 step of algebra, so that's just a little trick I have. In any event, that's number 6. Hopefully you solved this triangle and had no difficulties. That's it for number 6. Hey folks, here in number 7, you were asked, does this information, does it give you 0, 1, or 2 triangles? And you were asked to explain. This is that so-called ambiguous case, the law of sines. And just like in number 6, I start off by drawing a generic triangle. put in what I know. And I even put the same like solution area where my final answers will be. I know the book and all books will call this the ambiguous case, and I call it the so-called ambiguous case because really there's nothing ambiguous about it. If you draw a triangle and you have something like this set up, you are looking at no choice. You can't find angle C, you can't find side C. Because in order to find angle C or side C, you would have to know one or the other. You don't. You have no choice at this point in time. You must find angle B first. And to do that, you have to use the law of sines. This is a warning. When you find yourself being to first find an angle using the law of sines, I want that to communicate to you there could be problems here. There could be 0, 1, or 2 triangles. So I am forced to find an angle first using the law of sines. Don't have a choice. So to find angle B, I write down sine of B over little b equals the sine of A over little a. Notice I'm trying to find an angle, so I put that angle part in the numerator of the fraction. A little different than what I did in number 6. I'm just trying to save myself one step of algebra. I substitute in what I know. And I have, the sine of B over 13.6, side B is 13.6, is the sine of 52.1 degrees over 13.3. At this point in time, let me tag it up here. At this point in time, I would multiply both sides of the equation by 13.6 to get sine of B equals 13.6 times the sine of 52.1 degrees over 13.3. And here comes the key, the crucial step, and kind of not making this so ambiguous. Use your calculator. Crank all these numbers through your calculator. See what you get. When I crank this through the calculator, I get 0.85856. I'm just going to stop there. This equation, this line right here, it's an equation. This is a really important line. Here's why. If this number happened to be larger than 1, I'm done. There'd be no solution to the equation. If there's no solution to the equation, that means there would be 0 triangles. I want to see this equation because that tells me if I have 0 triangles or at least 1 triangle. So if this number were larger than 1, I'm done. No solution, no triangles. If this number is less than 1, as it is here, I know I have at least 1 triangle. So I proceed. Right now I know I have at least 1 triangle. So I proceed to find angle B. Angle B is the inverse sine of that 0.85856. And I get angle B to be, say, 59.2 degrees. So I know that's an angle that will go in here to give me a triangle. But, you know, this is almost like what we did back in, don't remember, number 5. Number 5, part A. This is looking very similar to when we solved those little trig equations that look like this. There's another angle in the unit circle that would have that as a y-coordinate. So that means there's another angle B that would make this equation a true statement. you find that other angle B by subtracting this 59.2 degrees from 180, and that gives you 120.8 degrees. So here's where we're at. I know this angle, 59.2 degrees. I know that comes in here and produces at least one triangle. This other candidate for angle B, which is 120.8 degrees. If I put 120.8 degrees in here for B, and I add it to A, do I get a sum that is less than 180 degrees? If the answer to that question is yes, then that means I have two triangles. If the answer to that question is no, if I put this angle, if I put that number in here and I add it to the given angle and it's larger than 180 degrees, then that means there would only be one triangle. But notice if I put 120.8 degrees in here for B, 120.8 plus 52.1 is 172.9 degrees. That is less than 180. So there are two possible triangles for this given information. Triangle number 1 would have that as an angle B, 59.2 degrees. Triangle 2 would have that as an angle B, 120.8 degrees. In both triangles, you would have the same angle A, the same side A, and the same side B. The only thing that would differ between the two triangles are angles B, C, and side C. So to recap, when you find that you have to find an angle first, using the law of sines, be worried. 0, 1, or 2 triangles. Crank through the law of sines, and I'm going to star this equation. I think this equation is it's so damn important. It's the key. If I have an equation, sine of B in this case, if I have a number over here that's larger than 1, I'm done. No triangles. If I have a number that's less than 1, I know I have at least one triangle. There could be two. Find the angle B that you know guarantees the one triangle. Find the other candidate for angle B, 180 minus that angle, and see if this other candidate plus the given angle is less than 180. If it is, you have two triangles. If it isn't, you only have one triangle. That's it for number 7. Hopefully you got it. Hopefully you see this ambiguous case really isn't that ambiguous. All right, folks, here on number 8, got a word problem. I think the most difficult part's drawing the picture. It says you have Coast Guard Station Zulu that's located 120 miles due west of Station Alpha. There's a ship out at sea that sends an SOS call, and it's received by each station. The call to Station Zulu indicates that the bearing of the ship from Zulu is north 40 degrees east. The call to Station Alpha indicates that the bearing of the ship from Alpha is north 30 degrees west. So how far is each station from the ship? So let's see if I can get a picture drawn here. We have Zulu, so I'm going to say here's Zulu. If I can spell Zulu. It says Zulu's due west of Alpha. So that means they're on the same east-west line. And it said they're 120 miles apart. So we know they're 120 miles apart. Now there's a ship out at sea, and the bearing, since an SOS call, the bearing of the ship from Zulu is north 40 degrees east. So here at Zulu, if I put in a north, south, east, west template, it says the bearing is north 40 degrees east. So that, remember bearing, I start at north, I come 40 degrees towards the east, So out here somewhere is that ship. So this is the sea. And this angle measurement here is 40 degrees. From Alpha to the ship, the bearing was north 30 degrees west. So if I put in that nice north, south, east, west template here, it's north 30 degrees west, so I go 30 degrees towards the west. And let me put, there's 30 degrees. So what is the distance from each station to the ship? So if I call this A, this side B, you're just trying to find the length of those two sides. Now let's see. We have this as 40 degrees. I think this angle here, well, it better be 50 degrees because it's a 90 degree angle from north to east. Likewise, this angle here is 60 degrees, which means this angle up here, if I add those two angles together and subtract from 180, I get the angle up there is 70 degrees. So all I have to do is find side A, side B. Well, I think to get side A, see, it looks to me like a law of sines problem. A over the sine of 60 degrees equals this side here, 120, over the sine of 70 degrees. And if I multiply both sides of this equation by the sine of 60 degrees, and then I use my calculator, I will get A to be about 110.6 miles. So that's the distance from Zulu to the ship, is 110.6 miles. Side B, similarly, I find it by using the law of sines. B over the sine of 50 degrees is equal to 120 over the sine of 70 degrees. And if I multiply both sides of that equation by the sine of 50 degrees, then use my calculator, I get side B to be 97.8 miles. So I guess the answer to the question, I would say from Zulu to the ship, it's 110.6 miles. From Alpha to the ship, it's 97.8 miles. So that's a pretty straightforward application of the law of sines. Hopefully you got that, because that's it for number 8. All right, folks, here at number 9, you're asked to solve a triangle, and you're given the length of the 3 sides of the triangle. So again, I sketch a quick generic triangle, and see A is 18, B is 14, C is 13. I need to find, I need to find the measure of all 3 angles. Now look, before I do any work at all on this problem, I know angle A is going to be the largest angle because side A is the longest side. And I know angle C is going to be the smallest because side C is the shortest side. This is a classic, a very typical law of cosines problem. Keep in mind with the law of cosines, or let me rephrase it another way. If you're given the measure of 3 sides of a triangle, there's only one triangle you can draw that will have the length of those 3 sides. That's the side, side, side case. If you're given 2 sides and the included angle, the side angle side case, there's still only one triangle you can draw. So there's no ambiguous part for law of cosines. For the given information, there is only one triangle. So here, I'm given the measurement of all 3 sides. These would be my guidelines for you. If you are given the 3 sides, find the largest angle first. It's going to save you a lot of grief. Just find the largest angle first. So here, that angle is angle A. So I'm going to find angle A first. And I'm going to use the law of cosines. I know your book talked about alternative forms of the law of cosines. Here's what I know as law of cosines. A squared is equal to B squared plus the C squared minus 2BC times the cosine of A. You know, and I know there's an alternative form that you could write down where you have cosine A equals A squared minus B squared minus C squared all over negative 2BC, whatever. If I know this, all I have to do is substitute in what I'm given. I mean, side A is 18, so I have an 18 squared. Side B is 14. Side C is 13. 2 times a 14 times a 13 times cosine A. And this is just, it's just straightforward, like number crunching. I'm going to skip some steps. But I would do 18 squared, the 14 squared, the 13 squared, the 2 times 14 times 13. I would add these two numbers together. And when I add those two numbers together, I think I get a 365. And I would subtract that 365 from both sides of the equation to get negative 41 equals, and then when I multiply this junk out here, I get negative 364. Divide both sides of this equation by a negative 364. Now look, a negative divided by a negative is a positive. And then to find angle A, I use inverse cosine. So I do inverse cosine of 41 over 364. And that gives me angle A is about 83.5 degrees. So at this point I know angle A is 83.5 degrees. Here's why I want you to find the largest angle first. Since I found the largest angle first, I know it's a guarantee angle B and angle C have to be acute angles. That's the largest angle. These angles are going to be smaller than that angle. They have to be acute. Because I know they have to be acute, rather than use the law of cosines to find angle B or angle C, to me it's a little shorter, quicker, easier to use the law of sines. So I would now use the law of sines to find either angle B or angle C. Here I picked angle C. And I'd use the law of sines. So I have sine of C over little c is equal to the sine of 83.5 degrees over 18, angle A over little a. And then I multiply both sides of that equation by 13 and then do inverse sine, and I get angle C to be 45.9 degrees. Okay. In case you're wondering, why am I not worried? I was using law of sines to find an angle. Why am I not worried about the ambiguous case of the law of sines? Well, I'm not worried because there's nothing ambiguous here for me to worry about. I wasn't first forced to find an angle using the law of sines. I found angle A first using the law of cosines. Another reason, there's only one triangle you can draw that has these lengths. You give me three lengths. You give me a triangle and the length of all three sides, I know there's only one triangle. Nothing ambiguous there. There is one triangle. Secondly, or thirdly, excuse me, once I found this angle was 83.5 degrees and it's the largest angle because it's opposite the longest side, I knew these two angles had to be acute. So I know that's the only angle that can work here. And then finally, let's finish the problem. To get angle B, simply add angle A and angle C. take that sum, subtract from 180 degrees, and you'll get angle B is 50.6 degrees. So, if you're given the measure of three sides, use the law of cosines, find the largest angle first. If you were given side angle side, use the law of cosines to find the missing side first. Then use the law of sines to find the smaller of the two remaining angles. And that's pretty much it for number 9, plus a little bonus information. So hopefully you have that. Hopefully you're all dialed in, and we're ready for the last one, number 10. All right, folks, number 10. It's another application. It says 2 planes take off from the same airport at the same time using different runways, which is probably good. One plane flies at an average speed of 500 miles per hour on a bearing of north 32 degrees west. The other flies at an average speed of 420 miles per hour on a bearing of south 20 degrees west. How far are the planes from each other 2 hours after takeoff? Okay, the hardest part, I think, drawing a picture. So let me just say there's the airport. And if I make my north, south, east, west template, I know one plane took off north 32 degrees west. So I start at north, come 32 degrees towards the west. So that's the one plane. That's 32 degrees. The other plane was at south 20 degrees west. So south, I come 20 degrees towards the west. There's the flight path of the other plane. I know this plane was traveling at 500 miles per hour. So after 2 hours, it will have gone 1,000 miles. This plane is cruising along at 420 miles an hour. So after 2 hours, it will have gone 840 miles. So the question is, how far apart are these two planes? What is this distance? We can just call that an A. It almost looks like it's a basic law of cosines problem. I know the length of this side. I know the length of this side. This is 1,000 miles. That's 840 miles. If I could just determine the angle measure, that's the included angle. Side, angle, side. And I can quickly find the measurement of this angle. I know this little angle is 32 degrees. This little angle here is 20 degrees. From north to south is 180 degrees. That's a straight angle. So I just have to add these two together to get 52 degrees. Subtract that from 180, and I get this angle in here, this big angle, is 128 degrees. Basic law of cosines application. A squared is equal to b squared plus a c squared minus 2bc cosine of A. Substitute in what I know. A squared equals 1,000 squared plus 840 squared minus 2 times 1,000 times 840 times the cosine of 128 degrees. Just barely got the degree symbol on there. And I get a squared, I get a, this is a big ugly number. I'm not going to write down that big ugly number, but once you get that big ugly number, you're going to take the square root of it to get A is 1,655.3 miles. And again, I think the most difficult part is drawing the picture. Once you get the picture drawn, it should be pretty straightforward. Well, folks, that's it for number 10. Hopefully you found this video solution to the practice test to be beneficial. More importantly, I hope that you're getting all the correct answers, and I hope you're really feeling confident for test 3. That's it. Thanks for watching, and good luck on test 3.